Next, let's copy and paste this line first, nnet. Okay, copy and then paste the R. Okay, so it does something. Okay, it does something. So let me look at one by one. First, this IBM nnet. This is the I want to store the result of the estimation, neural network estimate, into this one IBM.nn. Here we have this one. We have a lot of input over here, but they are not so difficult. Okay. In order to understand this one, we can use this one. We downloaded this material, right? The manual for nnet. So we can go to this manual for nnet, which is in the desktop. So let's click nnet, right? So there is a package nnet, and then here let's look at nnet, right? Function nnet. So here, fit neural network. So what nnet does, it fits the neural network. The usage is like this. There are two ways of using this nnet package. The description is it fits single hidden layer neural network, possibly with skip layer connection. What it means? Okay, in our neural network, okay, neural network example. In this case, it is a single layer, single hidden layer. We have just one hidden layer over here. What if double hidden layers? That's easy. We can move this one over here. Oops. Again, we can move this one. Okay. Move this over here. Somewhere over here, and then we can simply create another hidden layer. You can simply select another hidden layer. Okay, and then second hidden layer. Let me use this purple. So we can use another hidden. We can create another hidden layer. Hidden layer 1, 3. Now this is the first hidden layer. First hidden layer. This is second hidden layer. And then node between hidden layers. So we can do the same one. This one goes here, 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 like this one. Oh, this one, and then this one, this, right? Same. This is hidden layer. We can stack more hidden layer. In case of Google, when Google develops AlphaGo, AlphaGo is the Go playing artificial neural network. I heard that it is 9 hidden layers. Okay, in this case we have 2 hidden layers. But in case of nnet, let's go to nnet. Nnet can does only single hidden layer neural network. So with nnet, we cannot do this one. Okay, if you want to build more hidden layers, you have to use different. You have to use different package. Second one is that. Okay, second. Single layer, and possibly with a skip layer connection. What is a skip layer connection? Skip layers that it connects input output directly. So here, okay, let's delete this part because in nnet we cannot do hidden layer. So let's delete this one. Right, in nnet we cannot do this one. So let's move this into the again. Oh, this is the. Let me do it again. Yeah, hidden layer. Okay, and a skip layer means that we can connect from here to here directly. So if we want to do the skip, let's use yellow. Skip is from here. The skip layer is that yellow. From here to here, we connect it directly. Skip. From here to here. Here to here. So we have 3 more relationships. So we have 9 relationship here, 3 relationship here, 3. So now we have 15 relationship, right? So in nnet we can use this skip. Okay, skip. And that is, and that we have this one, x, y, weight, size. Full explanation of this one, you can read this one. Okay, there is explanation. So let's go back to our code. Okay, first nnet, first IBM x. This is x variable, so this is x variable. So we will use this information in order to predict y. So it is input. This is their the value data for input layer and their value for output layer. And then size. So it is x. This is y. So we use this one to predict this one. Okay. And I say size equal to, size is the number of size here. If you go to size, where is the size? There is an explain size. Number of units in a hidden layer. In the hidden layer, number of units can be 0 if there are skip layer units. So here I said size equal to. So in this case, well, I have to calculate 1 because in this case we have 3 units, right? In this hidden layer, we have 3 units. So if you really want to estimate this one, this neural network, what you have to do is, we go back to our code. And then we have to change it into the 3. Okay? Then we have 3 units in the hidden layer. If we set this size equal 4, it means that we have to add one more. We have to add one more here. Okay, if we add one more here, then it becomes 4 units per hidden layer, right? And then we have a more complex relationship, right? Let me focus on only 3 units in the hidden layer. So let me stick to 3 over here. Okay, and the line out equal t. Line out is, go back to again, then line out, switch for linear output unit, default logistic output unit. Well, if you set line out is t here true, then it gives you value some number. If you set this one as false, then it gives you predict as true or false. Okay, I'll explain this one in detail later. Okay, and then skip equal false. Let me say it is false. Okay, here false. Skip means that skip. Okay, here skip. Switch to add a skip layer connection from input to output. So if you want to take into consideration from here to here directly, you set this one t. Okay, t. But if you don't want to take account of this direct relationship from here to here, then you set it false, f or false, it doesn't matter, f. And in this case, to make matter simple, let's make it false. And then maximum iteration, max is maximum iteration. So it uses routine, so it does calculation up to 10 to the power of 4, like 10,000 times. It does the iteration up to 10,000 times in order to estimate this neural network. Then decay, relative tolerance, absolute tolerance, and range, they are all the values. You can check what it means in this information. Okay. I think this particular two, they are particularly important. That means tolerance. So if you make this number very small, and then your neural network becomes more and more accurate, but it takes more time to estimate. And if you make this number large, then the estimation time is quick. The computer estimates neural network quickly, but it is less precise. Okay, so let's copy and paste this one into our R. Okay, and it converged. Somehow it estimates something. And then in order to check the output of this IBM nn. Again, we just estimate neural network, and the information about the estimated neural network is stored in the IBM.nn. If you want to take a look at it, you can just a summary IBM nn, right? And it shows the relationship. Let's take a look at it. It is 331 network with 16 weight. Okay, what do you mean? Okay, here. Okay, well, this is complicated, so let me open new one. Okay, so here we have, let's go back to, let's capture this one, format. Oh, it's not possible. So anyway, okay, so this one, let me copy this one, and then go to this one. Oh, it is the, okay, output. Okay, let me interpret this one. So it is a 3. Okay, it is the first. This is very interesting one. First it is a 331. Okay, it is a 331 network with 16 weight. So it is the 1, 2, 3 input layer, 331. So 331. So it is 3 input layer, no, 3 input unit, and 3 unit in the hidden layer, and then 1 output. Okay, so this is the basic structure. Okay. Okay. Okay, so we have again 9 relationship over here, 9 relationship, and we have here 3 relationship. Sorry, yellow is too bright, so we have 9 relationship and 3 relationship. But here it says that we have 16 weight, right? Why it has 16 weight? Well, basically we will add constant. So again, this is RT, this is R, this is RT, and this is R yesterday's return, RT minus 2, RT minus 3. But it seems that there is a possible trend. Maybe there is a possible trend in the return. So here we want to add a constant term. Okay, constant term over here. So it is constant. So it is basically, you can regard this as input of 1, but it's mainly constant, right? So from hidden layer to output layer, maybe there is a constant term. There is maybe trend. So if we add constant term, so constant means is that suppose there is no hidden layer. Basically our relationship is RT is alpha 1, RT minus 1 plus alpha 2, RT minus 2 plus alpha 3, RT minus 3, right? This is one relationship between from 3 input to 1 output, but maybe there is some constant term, right? So we want to take into account something like this one. Something like this, some trend term, okay? So that's why we add constant term. Let me delete this one. So if we add constant term, from this constant term, right, it is all again connected to this one, right? But again, this is constant, this one, this link doesn't exist. Okay, doesn't exist. So from constant it goes 3 units. So plus 3. Now from input, now it goes again output because constant sum, so plus 1. This is plus 1. Now so it is becomes 9 plus 3 is 12. 1, 3 plus 1, so it becomes 4. So 12 plus 4 plus 16. So we have 16 way. That's why we have 16 way, because we take on a constant sum. Okay. So in this case, our SMS is linear output unit. Linear output unit. So we will see what it means shortly. And decay is default value. So the relationship is from here to, so this is a mathematical relationship. This is the estimate of multinomial logic model. But you can understand this one without knowing the multinomial logic model. Here, this H1, right? This H1, 82, 83 is the, here, this H means hidden layer. Hidden layer. Here I, we have also I, right? I means input layer. Input layer. Okay. B is the constant. B is constant. Okay. So the first one, B to H1. Let's call this one H1, H2, H3, and this is B, and this is B. Here this is I1, input unit 1, I2, I3. Okay, so here B to H1, B to H1, this one, this weight of this relationship is 8.01. Okay, use black one. And this one, second one, I1 to H1, I1 to H1, this relationship. I1 to H1 is about 16.3. Okay, let's take a look at this one. This one is I2 to H3. So I2 to H3 is basically this relationship. Weight of this relationship minus 3.37. Okay, how about this one? To H1 to O. Okay, H1 to O is H1 to O here. H1 to O. This one is 20.56. So it means that when this value increases, this one value tends to decrease. Okay, this is a positive. So when this value increases, this value tends to decrease. When this one increases, this value tends to decrease. Okay, it means. So you can read this one. So this weight means actually this strength of. You can regard this as a strength of each node. Okay, let's clean it up. Okay. Now, compute print the residual sum of squares. So let's see the prediction. Okay, let's see the prediction. So here it is predict. Now what we do is that, okay, we want to use this estimated neural network to know the prediction in sample. So we know the exact value y, but if we put this ibm.x as input variable and plug this one into neural network, it should generate some prediction. So let's take a look at this one. Y hat. Okay, so type y hat, right? So basically it is our prediction for stock return. Okay, so we have this value because it's line out. On the other hand, let's go to this one. If we change this line out as a false, let's change this one false. Okay, false, and copy and paste over here. Okay, and then if we use this y hat, then y hat, it basically gives you value between basically 1 or 0. Okay, like 1 or 0. Right? So this one is the close 0 and close 1. So it gives you value between 0 and 1. So it normalizes. Okay, normalize between 0 and 1. So we have a very negative number, then it is close to 0. It is very positive return, it becomes close to 1. So for every prediction, we match that number to the number between 0 and 1. So it is like a normalized prediction. In case of stock return can have any value from positive infinity to negative infinity. So in that case, therefore, we can set simply this line out as true. Okay. But if you are interested in estimating some like a binary value or some value between only between 0 and 1, you can set this one as a false, and then you have output. Okay, so anyway, let's learn this part again. Go ahead. Okay, go ahead. Now we can use this one. So tail. Yeah. In this case, we bind. Let's take a look at one by one. So to check our estimation, we want to match first y is our real data. Okay, real return. Y hat is our estimated return. We estimate this on IBM X, so it is input, our estimate, and real one. If we have a good neural network, this Y and Y hat should be similar to each other, right? If our neural network is not so good, then this Y and Y hat would be very different. Okay. And then let's take a look at this. Again, this is too long. So let's take a look at only head, first 6 law. Right, for 6 law. So it is Y and it is our estimate. So if you take a look at compare each other, well, they look kind of different. So it means that our prediction is maybe not so good. Okay. And you know, stock return is very hard to estimate, so it is not surprising that this line and this line looks different. Let's take a look at the last 6 items. So head, instead head, let's type tail. Click this one. Then we have the last 6 items, and then they are real data, and this is our prediction of this one. And actually in our prediction it doesn't even match positive and negative. It is positive stock price go up, stock price go down. It always says stock price always go up. Well, so it means that our estimate may be not so good, and this is input variable. And then okay, so this is Y and Y hat, and then again we want to make this one as close as possible, right? If our neural network is very good, this one should be very similar to this one, right? And how to measure the distance between this one and this one? Well, we can regard this entire thing as a vector, entire Y as a vector, entire estimate, which is I hat as a vector, and we can measure this distance between these two vectors, which we can do this way, like SST. SST, squared sum of squared, this is very clear, squared sum of errors. What does it mean? So we measure distance y and y minus head. So y minus head is the distance between the two, a gap, and we square it. Okay, and so it is squared sum of square. So if our prediction is good, this one should be small, right? If it is not, this number becomes large. And then copy and paste, and then see, square the sum of errors about this one. If you want to know the average, you can divide this one as the length of the y, length over 42. Actually, length of y hat over 42 to 6. Okay. So this is kind of big. Now we want to set up the input variable in the forecasting subsample. As you can remember, the length of our data, let's take a length of our data is 888. However, when we estimate data length y, we use only 861. There is a reason for that, because we saved some fraction of data for out of the sample test. Okay, this SSE is the in sample squared sum of errors. So it is in sample. Okay, so it is in sample. But we are interested in the performance of our neural network outside of our estimation data. So we will use new data. Which we didn't use to estimate the neural network. So we get the new data, and then we want to check the performance of this neural network in that new data. Okay, the next code is for that purpose, and then we will do this one after the break.